So let us start them.
Yes, please.
Yes, sir.
Let us
Thank
start.
you, Dr. Ajit Prabhu.
Sir. Good afternoon. We have all assembled to pay homage to our beloved scientist, Professor Thanu Padmanabhan, who breathed his last on 17 September morning. He was one of the promising scientists of the country, an eminent theoretical physicist and cosmologist. His research spanned a variety of topics in gravitation, structure, formulation in the universe, and quantum gravity. He was an Indian scientist who unraveled the mysteries of the invisible universe and explored the heart of darkness. He tried to get an answer for the research question, how did structures like galaxies, clusters of galaxies, etc. form? He wrote in his homepage, I worry a lot about putting together the principles of quantum theory and gravity in a consistent manner. That was always a pressing issue for him. A true scientist who knew infinity and played with the complex Big Bang theories. His departure is a shock and loss to the scientific fraternity. I feel that he will shine as a bright star among the billions of stars among the galaxies in the ever expanding universe. Salutations to him and pranam. This 1 week long commemorative webinar series is organized by Kerala State Council for Science, Technology and Environment in association with Kerala University, MG University, Cochin University of Science and Technology, and Calicut University in Kerala. This program is attended by faculty members, researchers, and students and in the physics department and other colleges, and also scientists from R&D institutions in the Kerala state. The state level webinar series program starts today with an inauguration by the Honorable Chief Secretary to the Government of Kerala, Dr. VP Joy IAS, representing Government of Kerala. In the function presided over by Dr. S. Pradeep Kumar, the Member Secretary of KSCSTE. Respected Dr. Somak Ray Chowdhury, the Director of Ayuka, has kindly consented to share his memories with us, followed by the memorial lecture by Dr. L. Sriram Kumar, Professor of Department of Physics, IIT Madras. By IAS, the Honorable Chief Secretary to the Government of Kerala is a Malayalam poet, writer, researcher, and administrator. He is also known for books and research papers on the energy policy and also on philosophy of education, mind, and metaphysics. He has published several literary works in Malayalam language, mainly poetic compositions. During his official career, spanning more than 3.5 decades, starting as scientist in Vikram Sarabhai Space Center under ISRO, he has held important assignments in the Government of India as well as in the state government of Kerala. Being a technocrat, he has proven himself to be an efficient bureaucrat too. He is always found passionate about the scientific activities of Kerala and highly supportive to KSCSTE. Sir, on behalf of KSCSTE and all the universities collaborating with this program, with great honor and respect, I welcome you to this function, sir. Dr. S. Pradeep Kumar, the Member Secretary of Kerala State Council for Science, Technology and Environment, is providing continued support for all the scientific programs during the last 5 years and is presiding over this function. Sir, on behalf of the organizers, I welcome you to preside over and moderate the program.
Thank you.
Dr. Somak Ray Chowdhury, an Indian astrophysics physicist and director of the Inter-University Center for Astronomy and Astrophysics, Pune. He is from Presidency University, Kolkata, and known for his work on stellar mass black holes and supermassive black holes. His significant contributions include those in the fields of gravitational lensing, galaxy dynamics, and large-scale motions in the universe, including the Great Attractor. It is noteworthy to mention that Dr. Somak Rai Chowdhury has kindly consented to share his memories over a single phone call in spite of his busy schedule of activities, and that is the affection he has with Professor Thanu Padmanabhan, who was his colleague. Sir, on behalf of the organizers, wholeheartedly I welcome you to this function. The memorial lecture is delivered by Dr. L. Sriram Kumar, professor and a member of the Gravitation and Cosmology group in the Department of Physics, IIT Madras. It is worth mentioning that he took PhD under the guideship of Professor Thanu Padmanabhan from Inter-University Center for Astronomy and Astrophysics. Sir, on behalf of KSCSTE and the organizers, I sincerely welcome you. The webinar series is jointly organized with various universities in Kerala state, and I take this opportunity to welcome all the honorable vice chancellors, HODs of physics department, and all other faculty and professors and students and researchers who are attending. Last but not least, I welcome all my colleague scientists, all staff of KSCSTE, and especially Dr. P. Harinarayan, who is the coordinator and giving vote of thanks today for this week-long program. Thank you. Now may I request Dr. S. Pradeep Kumar, the Member Secretary of KSCSTE, to offer presidential address and moderate the function, sir.
Thank you, Dr. Ajit. Honorable Chief Secretary of Government of Kerala, Dr. V.P. Joy, Dr. Somak Rai Chowdhury, Dr. Sriram Kumar, Dr. Ajit Prabhu, Dr. Harinarayanan, my dear friends and colleagues. World's most renowned and eminent theoretical physicist and cosmologist, Professor Thanu Padmanabhan, is no more with us. We are gathered here today to pay tributes and condolences to the departed soul and to discuss his contributions. He was a native of Thiruvananthapuram and did his schooling at Model High School and his graduation and post-graduation from the University College, Thiruvananthapuram. Then he joined the Tata Institute of Fundamental Research for his PhD and became a faculty before the completion of his doctoral studies. After a spell of period at TIFR, he moved to Pune and began his long and fruitful association with the city-based Inter-University Center for Astronomy and Astrophysics, where he became a distinguished professor and served as Dean for academic programs. His significant contributions are in the areas of gravitation, quantum gravity, and structure and formation of the universe. Professor Padmanabhan has authored several advanced level textbooks which are acclaimed as magnificent achievements and used worldwide as standard references. Apart from his scientific research, he has given many popular science lectures, several of which are available on social media, and authored more than 100 popular science articles published in various national and international journals. He has also authored many popular science books. Along with several other awards, he was also honored with Padma Shri. Professor Padmanabhan was recently selected for Kerala Shastra Puraskaram, an award instituted by Kerala State Council for Science, Technology and Environment, Government of Kerala, to honor distinguished scientists of Kerala origin. He was awarded for his lifetime contribution towards theoretical physics. In fact, we had during the coming November to honor him with the Shastra Puraskaram, but unfortunately he left us without waiting for that. He was the elected president of the Cosmology Commission of the International Astronomical Union and chairman of the Astrophysics Commission of the International Union of Pure and Applied Physics. He has also been a visiting faculty at many institutes, including the California Institute of Technology, Princeton University, and a second distinguished astronomer of the Institute of Astronomy, Cambridge. He is also the fellow of 3 National Academies of Science in India. We are organizing this commemorative webinar series to pay tribute to the country's great scientists. We have eminent scientists to deliver and share the memories with Professor Thanu Padmanabhan. His life as well as contributions will be an inspiration for the budding scientists. His dedication to this field of his interest is remarkable and is visible from his publication and activities. With this, I stop here and wish this webinar series a grand success and all the best the organizers of this webinar. Thank you. Thank you all.
May I now request Dr. V.P. Joy, Honorable Chief Secretary to Government of Kerala, to inaugurate the function. Sir.
Dr. Pradeep Kumar, Member Secretary of Kerala State Council for Science, Technology and Environment. Dr. Somak Ray Chowdhury, Director, Inter-University Center for Astronomy and Astrophysics, Pune. Dr. L. Sriram Kumar, Professor, Department of Physics, IIT Madras. Dr. V. Ajit Prabhu, Chief Scientist, KSCSTE, and all other distinguished scientists, academicians, and all distinguished persons gathered here. We are very much saddened by the sudden demise of the most honored Dr. Thanu Padmanabhan, a legendary scientist of our country. While we take pride in the fact that he hailed from Trivandrum and was a student of the University College here, we are greatly grieved by the fact that such a great scientist who would have brought laurels to our country in his area of research, a well-known authority in astrophysics and cosmology and related areas, is no more with us today. If we look at the contributions of Dr. Padmanabhan, I'm sure that as time passes, some contributions will become brighter and brighter, some names will become brighter and brighter. That is a phenomenon which it is a deterministic phenomenon. Just like the world is revolving around a destiny that we cannot prevent nor postpone. But after that, there are several personalities, the light and the legacy which they leave gets dwindled. For a person like Dr. Thanu Padmanabhan, I'm sure that as time passes, his name and his contributions will grow more and more and will lighten up the areas of knowledge which he handled with such expert eminence. Now, when we hear through some of his talks, some of his ideas, he mentioned that he is doing research not for any kind of remuneration. He said that even if his salary is cut, I mean, he is not given any salary, still he will continue to do the same thing, same work in the same manner, provided he is given enough to survive. This is one statement which he made. When I heard about it, I remembered, the words of Albert Einstein, whose legacy he tried to carry forward. Einstein said that the cosmic religious experience is a fundamental driving force behind the scientific research. I would like, perhaps he intended spiritual experience. Cosmic spiritual experience is a fundamental driving force behind scientific research. It has been mentioned that the two things terrify. I think one is the starry heavens above, and the other is the moral law within. This was spoken by none other than Immanuel Kant. There are two things which terrify us. One is a starry heavens above, and the other is a moral law within. So, from these kind of mysteries in the world, when those things are probed, it gives a kind of cosmic spiritual experience. And in order to get that glimpse of spiritual experience, people are willing to devote their life to find the truth. And truth in matters of science, as Galileo stated once, in matters of science, the well-considered opinion of one individual is more worth than the prejudices of thousands of people. Now, with this kind of experience which he was trying to pursue, the dead ends of physics after Einstein's general theory of relativity came into vogue in 1916. The people were always after finding the equation, the theory of everything, so-called theory of everything, which can explain all the four fundamental forces. And that was found to be a very, very tough problem, very difficult problem, and very complicated problem. Because often it is said that simplicity is a kind of beauty, in a way. It has been said that general theory of relativity is the most beautiful theory ever formed so far. Because the beauty is also, perhaps, I don't know, there is no proof that beauty has any connection to truth. Whether beauty assures truth of anything is debatable, and vice versa. Whether truth will assure beauty is also debatable. In which case, a lot of people, then the most handsome person in the world would be perhaps Mahatma Gandhi, who did a lot of experiments with the truth. And so beauty and truth apparently is not that much connected. But still, there is some kind of inherent connection also. Because beautiful theories which are very much logical, which are perfectly, aligned ideas and concepts, they might have some truth element in them. At least we would like them to have, even if they may not actually have. But anyway, theory of relativity is the most beautiful theory when it was formed, and over a period of time, it was proved to be true also, because so many findings could be verified, whether it is in terms of bending of light or gravitational lensing or any other gravitational waves or any other such phenomena which could later on prove that theory of relativity is not only beautiful but also true. But how far it is true was challenged by this, the search for the theory of everything, which could not attain the finality. Because after all, theory of everything will show the truth. And as long as theory of relativity cannot merge and with other theories and produce a theory of everything or explain everything, it cannot be considered to be completely true, though it may be the most beautiful. So, despite the search for many, many years, people thought that now we should start searching in some other direction. Because any search which makes it excessively complicated, excessively complex to explain more and more of the phenomena which are observed, then there is a likelihood that things may not be true. Because the nature, so many things are told about nature. There is a universal law of cosmic laziness. There is a law of that nature will abhor vacuum. Now, nature will abhor complexity. I don't know whether there is a law like that, but at least we would like to prefer some such law where we would search for simplicity and would like to have simple things, which when things are as simple as Newtonian equations of motion depict, forces far away and far apart, then we are very happy about it. So we want simplicity also. So with all these various kinds of models where we try to integrate quantum physics with general theory of relativity, people were getting fed up. Things were becoming more and more complicated, leading to nowhere. And that is when Dr. Thanu Padmanabhan came and, of course, showed a totally different path by which the gravity was considered to be or depicted to be an emergent phenomenon. That was definitely a breakthrough and a new path which he brought out in the search for truth. And of course, his genius was in terms of connecting it to the classical theory of thermodynamics, whereby, initiated by Boltzmann and people like such scientists who have considered not, see, when from Einstein to, from Newton to Einstein, it was definitely a breakthrough. Something which was considered as a force, gravity as a force, was considered as, converted to a curvature of space-time, and the idea of force was removed by Einstein. Of course, it was a breakthrough in terms of the conceptual path in explaining the phenomena of the universe. But then Professor Thanu Padmanabhan came and again brought a conceptual revolution, that the curvature, what is interpreted as the curvature of space-time, is nothing but certain property of space-time which emerges, just like the thermodynamic phenomena emerges if the matter is assumed to have certain fundamental quantities or fundamental, things like atoms or molecules. A conglomeration of atoms and molecules, by virtue of their conglomeration, will bring certain properties, thermodynamic properties. So like that, he has even paved the way for, maybe people can now search for the fundamental particles of space-time. It is possible, because with such a fundamental particles of space-time emerges the so-called emergent phenomenon of gravity. So the things could be much easily explained, more beautifully explained, more elegantly explained, and things became simpler because of the ideas brought forth by Professor Thanu Padmanabhan. And I'm sure that as time passes, these ideas will be explored, no doubt. And when those ideas are explored, and when those ideas are found to be true, I'm sure that Professor Padmanabhan's contributions will become brighter as a time comes. It is interesting to note that for general theory of relativity, Einstein did not get a Nobel Prize. But there were people who got Nobel Prize because by finding out things which can prove general theory of relativity. For example, gravitational waves. The persons who detected gravitational waves got a Nobel Prize. But the persons and detected gravitational waves and proved or found out one proof for general theory of relativity got Nobel Prize. But the very person who invented that theory did not get a Nobel Prize because probably it was not proved during his period. Similarly, I'm sure that the paths which are shown by Dr. Padmanabhan, more researchers may come and they may get a Nobel Prize also. But the original ideas which were suggested by him will remain as the beacon of light in the search for truth. And we are assembled here today in his memory. And we wish that several eminent people, eminent academicians, scientists will emerge in our country to pursue his path and take the sciences to greater heights. I'm sure that the Kerala State Science and Technology and Environment has taken this effort to organize this webinar series in honor of Professor Thanu Padmanabhan, and it is definitely a very apt initiative of this council. So with today, I'm happy to note that as part of the webinar, several very distinguished academicians and researchers are giving commemorative lectures spread over a few days in the coming few days, and I wish and hope that this event, the legacy which Professor Padmanabhan gave to us, our young scientists, students, they will take them forward. With these words, I am happy to inaugurate this webinar series, and thank you all.
Thank you, sir, for your tribute as well as highly scholarly talk. Thank you. Let us now listen to the words of Dr. Somak Chowdhury, the director of IUCA. Sir, please.
Namaskar, thank you. Good afternoon. That was, I hope you can hear me.
Yes, yes, sir.
Yeah. Thank you very much, Dr. Joy, Chief Secretary, for your wonderful introduction to the subject and the work of Professor Padmanabhan. Thank you, Dr. Pradeep Kumar and Dr. Ajit Prabhu, for inviting me to this memorial meeting. Well, we are assembled here in a very, very solemn occasion to remember Professor Thanu Padmanabhan, who passed away on 17 September. We are still in a state of shock as a family here at the institute where he worked since 1992. We are a very close-knit group who work together and live together in the same community. And Professor Padmanabhan was there. I mean, this institute, the Inter-University Center, is a UGC institute that that was created in 1988 with Professor Jayant Narlikar as its first director, and who moved from the Tata Institute in Mumbai. And Professor Padmanabhan was his star PhD student, and then a faculty of TIFR who moved a few years later. So from the very beginning, he was associated with my institute here, and here he was the Dean of Academics for almost most of 2 decades. And he essentially set the standards of our academic standards as well as the way we run the institute. So it is very difficult for us to imagine our institution as well as our subject in a way without Padmanabhan's active participation. So we are shattered in many ways. IUCA is an institute which was set up so that faculty members and students from universities from all over the country can work with us and work with each other in this new emergent subject called astrophysics and cosmology, which is very new, not a common subject in Indian universities. And so when it was set up, very few universities taught this subject, and it's our duty to make sure that universities bring up this subject and then students get access to it. And the small core faculty, Padmanabhan played a very important role in making this happen, and in particular in Kerala, where he's a particular fondness for Kerala, where he's from, meant that Kerala soon became a very important player in Indian astrophysics.
Sir, it seems it has gone to mute this thing, sir. Kindly unmute, sir. We are not able to hear you, sir.
Shumak, we are not able to hear you.
Sunil, please.
Now.
Well, now it is here. Now it is audible.
Yeah.
I changed my microphone. Yeah. Okay. So I was saying that in particular in this whole job of getting the Indian academic community in astrophysics is a very interdisciplinary subject. It requires mathematicians, physicists, engineers, statisticians, and all kinds of engineering, computer scientists, all together to think about the universe, to understand and unravel the secrets of the universe. And in this way, all kinds of academic communities have to be brought together. And Padmanabhan played a very important role in getting the academic community in Kerala, in particular, and of course all over India, together with these jobs. And now you can see, look around in the state, and you will see many, many departments, many students having access to astrophysics and space sciences. And one of the major things was Padmanabhan's interest in this region. Padmanabhan set very, very high standards for himself and his students and people around him. And that high standard and hard work, very, very hard work, set our tone here at the Institute and whoever came here. And you will see this. Today we have a talk from Dr. Sriram Kumar, who was one of his PhD students, and later in the week you will see them talking about how uncompromising Dr. Padmanabhan was in setting this kind of academic standard. Prolific researcher, over 4 decades, he wrote more than 300 just peer-reviewed papers, as well as so many articles, popular articles. One of the most cited authors in India in physical sciences. One of the features, as Dr. Joy mentioned, is that he fearlessly tackled, like a warrior, the most difficult problems. He never had any time for easy problems. Many scientists go for what is known as low-hanging fruit, which means that it's easy to do. You get students to do things. Padmanabhan was just the reverse, uncompromising. He would go for the most difficult problems ever. And as was mentioned already, he was starting to think about how to combine quantum mechanics and gravity. And it's the hardest problem ever. I mean, Einstein didn't succeed in doing it, and he made some very important contributions to this. He also paid attention to how such things would be observed. So the observational aspects of theory. It's not just pure theory. So he very early on started paying attention to what is known as the cosmological constant problem, which now has emerged in cosmology as a very important subject, as dark energy, and Padmanabhan played a very important role in that, and also thought very deeply about basics of physics. Now, last Sunday we had a very interesting memorial meeting here at IUCA, where people from all kinds of backgrounds got together, and one of the things that was said repeatedly was that Padmanabhan's major contribution, not just it was to research, but also to write some of the most seminal textbooks in the subject. He wrote 16 books, out of which there are absolutely basic textbooks that all over the world students read in courses in astrophysics. Here now, if you have somebody entering Harvard University or Cambridge University and doing astrophysics, they have to read Padmanabhan's textbook, right? These are basic textbooks. In addition to that, he wrote some amazingly popular books. One of the best books in his popular books is called After the First 3 Minutes. The First 3 Minutes was the classic book written by Steven Weinberg, who also passed away a few months ago this year. And it's amazing that the author of the After the First 3 Minutes book, which came from that, very interesting, also passed away last week. So that and there were many others. Recently, he wrote a book with his wife on the history of Indian science, which included a whole chapter on Madhava and the Kerala School of Mathematics. Very, very interesting book, very well researched book, looking at the contribution of our tradition, Indian tradition in science. So those are important. And also, finally, I would talk about his very deep sense of humor he had. I've known Padmanabhan since 1986, when I was a PhD student in Cambridge, and he was spending a year sabbatical. He first came there, and together in that whole year, we spent a lot of time together. I learned a lot from him. He was just 5 years older than me, but he was already a faculty member at the Tata Institute, and he was spending a year in Cambridge. Learned a lot from him that time, and since then, in the last 35 years, I've learned a lot in many ways from him. Even now as director, when I went into a crisis, the first person I would call is Padmanabhan, saying, what do I do? Things like that. And so in that way, this is a very personal loss for me. But the sense of humor that came through actually comes through everywhere. It comes in his papers, comes in his books. He used to write a comic strip on science, on physics. In Science Age in the 1990s, if you remember, there was a magazine called Science Age. And then in our newsletter, for I think 15 years, he wrote a regular column on puzzles in mathematics. He used to play chess puzzles and mathematics puzzles, written in a very humorous fashion. This is what a scientist is. A scientist is not somebody who does something that is totally focused in one direction. An ideal scientist is somebody who sees the whole picture and does it in a fashion in which they can enjoy what they're doing. And Padmanabhan was the embodiment of this, of somebody who enjoyed doing what they were doing, did it in style, and also looked at the whole picture, not just one corner of a photograph, right? So this is where why this loss is so hard-hitting for us, that there are very, very few people in the world like him who can do this. I'd stop there. Thank you very much for letting me join in this celebration of his work, and we'd be very happy to get on with the lectures, the lecture series that you have arranged. Thank you very much, and my best wishes for them.
Thank you, sir. Ajit Prabhu, your mic is mute.
Okay, sir. Sir, thank you for joining us in sharing our feelings of sorrow on the sad demise of Dr. Thanu Padmanabhan. Thank you, sir. We know that you are coming amidst an interview board, so thank you for making it out. Thank you, sir. Thank you so much.
Thanks.
Now, let us move to the memorial lecture by Professor Lakshman Sriram Kumar, sorry. Professor Sri Kumar is the professor and a member of the Gravitational and Cosmology group in the Department of Physics at the Indian Institute of Technology, Madras, Chennai. Earlier, he was a member of the faculty at the Harish Chandra Research Institute, Allahabad, and moved to the Indian Institute of Technology, Madras in 2011. As already told, he took PhD under the guideship of Professor Thanu Padmanabhan from Inter-University Center for Astronomy and Astrophysics, Pune in 1997. He is postdoctoral fellow from Harish Chandra Research Institute, Allahabad, and also from University of Alberta, Canada, and also from Raj Institute of Physics, Hebrew University, Israel. He served as a fellow in Harish Chandra Research Institute, Allahabad, reader and associate professor in Harish Chandra Research Institute, Allahabad, associate professor, Department of Physics, Indian Institute of Technology, Madras. Sir, we are fortunate to have you with us today and request you to take over. Sir, please.
Thank you. Thank you very much, sir. Maybe I'll start sharing my screen, sir. You're able to see my screen, sir?
Yes, yes, yes.
I would like to begin by thanking Professor K.P. Sudhir, Dr. Ajit Prabhu, Dr. Pradeep Kumar, and the Kerala State Council for Science, Technology and Environment for organizing this webinar series as a tribute to Professor Thanu Padmanabhan, as well as inviting me to give a talk in the series. Professor Padmanabhan, affectionately known as Paddy to many of us, was an intellectual giant, and I was indeed fortunate and privileged to have had the opportunity to interact with him. The sudden demise of Paddy has been a devastating loss. Paddy, his wife, Dr. Vasanthi Padmanabhan, and daughter Hamsa Padmanabhan, has always treated us, his students of Paddy, as their family. To me personally, Paddy's passing away has been like losing a parent. He's irreplaceable. In this talk, I will speak about the work I've been carrying out over the last decade or so on issues related to the physics of the early universe. I'll focus primarily on issues related to inflation and reheating. Before I go on to discuss the physics involved, I will share some memories of Paddy as I have been requested to do so. Here is an outline of my talk. I will start with some memories of Paddy, as I mentioned, and then I will go on to outline the so-called cosmic microwave background and how it leads to this idea of the hot Big Bang model. And then I will explain this idea called inflation, which is crucial to my talk. And then I will go on to discuss observational constraints that emerge from the so-called CMB anisotropies. And then I will talk about formation of primordial black holes and gravitational waves, which have gathered considerable interest over the last few years since the discovery of gravitational waves from merging binary black holes. And then I will talk about, observational epoch, observational signatures of this epoch of reheating. And I will close with a very brief summary. I should clarify that I have planned this talk aimed at a general physics student and non-experts. And if there are any questions from experts, I'll be glad to answer it towards the end of the talk. Let me start with a few memories of Paddy. I distinctly recall many exchanges with Paddy. I will share a couple of them. The access to Paddy was simultaneously beneficial and challenging. Beneficial for the reasons that it helped one to raise one's own level, and challenging for the reason Paddy was very difficult to keep pace with. Paddy used to say, Sriram, you're working hard, you need to work smartly. I guess for lesser people like me, there was no option but to work hard to keep up with Paddy's expectation. This picture I'm showing here, if I remember correctly, was taken in November or December 1992, when Paddy had won the Birla Science Prize. It's one of the many awards he will go on to win. And this was taken at a time when I had just started working with Paddy towards my thesis. And it was Paddy who were introduced to textbooks by, for instance, Landau Lifshitz. For us students, I believe it set the standards of Paddy's expectations. And in fact, I distinctly recall meeting Paddy immediately after the interviews for selection for the IUCAA's PhD program. I had met him in the lounge at NCRA and discussing with him at some length about what I would like to do. And later I was very glad he could accept me as his PhD student. And this is a comment I had made acknowledging Paddy in my thesis in 1997 when I had sort of completed my thesis work. He is incredible. He's amazing. His enthusiasm and energy to discuss physics were always admirable. What is amazing is the fact that he carried on with this enthusiasm right until his last day. And I used to make fun of him about, his reluctance to exert himself physically. I recall, in those days I used to work out regularly, and he used to make fun of me. At some point of time, I had said, Paddy, look, there are a set of books about exercises that have come to the IUCAA library. There is a nice 6-volume of them. And interestingly, Paddy went on to read all of them. And I said, Paddy, you shouldn't just be reading them, you should try them out as well. And I recall him mentioning, look, Paddy, look, Sriram, I regularly raise and lower indices. You need to raise and lower indices when you're, encountering these objects called mathematical objects called tensors in general relativity. And he said, that is more than adequate exercise for me. And Paddy, I should also mention, was always close to his roots, and he enjoyed visiting Kerala to give talks and interacting with students. And I was at HRI Allahabad earlier, and I moved to IIT Madras about a decade back. And I considerably benefited from Paddy's visits to Kerala because he will typically stop over in Chennai before he traveled to Kerala. Paddy had made his impatience a virtue, as he has written in the prefaces of one of his volumes on the preface to his 3 volumes on astrophysics. He wished to cover as large an area as possible within a short span of time, much in the manner of Genghis Khan. Exact words, actually. Unfortunately for us, Paddy seems to have exhibited the same impatience in his final moments as well. Paddy's loss leaves behind a huge void in our lives. It'll take us quite a while for us to come to terms with it, but he will remain in our memories forever. With those remarks about Paddy, let me move on to the physics I would like to discuss in this talk. As I mentioned, I'm interested in understanding the physics of the very early universe, particularly these epochs called inflation and reheating. I will explain these epochs as I proceed with my talk. I'm sure all of you have heard about the so-called hot Big Bang model. It is the prevailing scientific model of a universe. And as this screen grab from this famous American sitcom, it's in fact the title song of the sitcom. The sitcom is named Big Bang Theory. As it says, our universe was in a hot, dense state. So according to this hot Big Bang model, our universe began in a hot, dense state, and it cooled down as it expanded. I'm sure you have already heard about observations that point to the expansion of the universe, and later structures, such as galaxies formed to become the universe that we see around us today. Why do we believe the universe, began in a hot, dense phase? We have matter around us. We see matter around us. We are made of matter, but there is also radiation around us. The radiation we are mostly familiar with is the radiation from the stars, but that doesn't constitute the largest amount of radiation in the universe. What has been plotted here is the intensity of the radiation as a function of wavelength. What one finds is that it is not, as I mentioned, it is not just the radiation in the starlight, etc., that dominates the energy density. It is something else that dominates the energy density in the universe. Energy density in radiation. It's cosmic because it is present everywhere, and its background, again, for the reason it is present, it acts as a background among which the galaxies sort of evolve. And it's referred to as the microwave background because it peaks in the microwave region of the electromagnetic spectrum around this region. I hope you're able to see my mouse. And amazingly, what one finds is that it's an extraordinarily thermal spectrum. In fact, it is a thermal spectrum that is unlikely to be bettered in the laboratory. We are bathed in this thermal radiation. Even as we sit, listening to my talk, or as I'm giving my talk, there are hundreds of photons which go through us, which correspond to this thermal radiation. And this spectrum, what has happened is that we have zoomed over a small range of this complete spectrum. And these are error bars, observations with error bars taken by the Kobe satellite. And these observations were made in the early 1990s. And it corresponds to a temperature of about 2.725 Kelvin. What I want you to appreciate is that these error bars, as indicated here on top, has been multiplied by 400 times so that they are visible in the slide. So this is an amazingly perfect black body radiation. And it is this black body radiation and the presence of the black body radiation and the fact that the universe is expanding that leads to this idea of the hot Big Bang model. So what happens is as follows. That the matter density falls as 1 over volume. As the universe expands, the energy density of matter in the universe falls as 1 over volume. In contrast, one can show using general relativity, basic arguments from general relativity, that the energy density of radiation goes as 1 over v power 4 by 3. In other words, it drops down faster than the energy density of matter. But if you track back, imagine a picture where the universe is evolving. Now you run this picture backward. What happens is as follows. As you go back in time, the energy density of the radiation rises faster than the energy density of matter. The energy density of matter is dominant today. In fact, that is not quite true. It is something else called dark energy that dominates today that Shomak referred to, but that is not relevant for our discussion, so we will ignore that. So you have matter and you have radiation. As you go back in time, the energy density of radiation dominates that of matter. And therefore, very early in the universe, you have a very hot epoch, and that is what is described in this picture as this yellowish fluid. You have matter as well, and these matter here in this diagram has been characterized as red balls, large green balls, and small green balls. The red balls are essentially protons, the large green balls are neutrons, and the small green balls are electrons. So think of the situation. You have a very hot universe. The universe is expanding, it is cooling down. When it was very hot, what happens is that these photons, that constitute this fluid, this yellow smeared fluid, has very high energy, and they will not allow these electrons to combine with the protons to form an atom. So for instance, this is a hydrogen nucleus. this is a helium nucleus. It contains 2 protons and 2 neutrons, while this is just a proton. But as the universe expands, as I mentioned, the radiation cools, and there comes a temperature where there is no adequate energy in the photons to knock off the electrons that combine to either a hydrogen, proton, to a proton forming a hydrogen atom, or to the, a helium nucleus forming a helium atom. What happens is that you say the matter present in the universe has essentially decoupled from this radiation at this epoch. It occurs, remember, the temperature of the universe today is about 3 Kelvin. So this occurs at a time when the universe had a higher temperature of about 3000 Kelvin or so. And thereafter, these photons that had constituted this fluid of radiation do not interact with matter at all, and they start streaming freely, and that is what we observe today as the cosmic microwave background. There is another way of understanding this cosmic microwave background. You're familiar with the cloud. You have photons present inside the cloud, and what is happening is that as it reaches, it is constantly colliding with, say, the water molecules that are present in the cloud. But as it reaches the edge of the cloud, it starts streaming freely towards your eye, and it is that photon or collection of photons that allows you to see the cloud as it is. In very much the same manner, you can look at different directions of the sky, and as you see in the different directions of the sky, in each of these directions, such a phenomena has occurred. This is in time. So what you have is that as you look at different directions of the sky, it is very much like a cloud here, beyond which the photons had a very small mean free path, much like the cloud here. They were not able to, traverse freely. But the moment they come to the edge of this surface, it's called the last scattering surface, for the same reason as this edge here is the last scattering surface for the photon before it comes to the eye. These photons emerge from this last scattering surface, and it is observed by us today as the cosmic microwave background radiation. And this cosmic microwave background radiation is usually characterized in the following fashion. Remember, you have a surface from which these photons emerge, and these photons, I should emphasize, hardly interact. There is many galaxies, etc., present, but the photons hardly interact with them on the largest scales, on the largest angular scales, and they come and reach us. And by observing them, we are able to understand what happened between the surface and this Big Bang singularity which lies behind it, and inflation, as we shall see, would have occurred somewhere in between. And how do you characterize the temperature of this cosmic microwave background, which I will refer to as the CMB? Remember, you have a spherical surface here. Remember, it's a spherical surface that encompasses in all directions, much like the surface of the Earth is captured through the so-called height of projection. What one does is that the temperature on the CMB sky is often displayed in this manner. And this is what are known as anisotropies in the cosmic microwave background, which I will comment about in a matter of minutes. This is one of the earliest pictures of this cosmic microwave background sky. And what you see is that the temperature in different directions of the sky is roughly the same. As I mentioned earlier, up till the 3rd or the 4th decimal place, the temperature in the different directions of the sky remains the same. It is about 2.725 Kelvin. What has been displayed are different temperatures in different directions of the sky. If all the sky has the same temperature, then you refer to it as an isotropic sky. But what is happening is that if you measure the temperature to the 5th decimal place, what you find is that there are differences in the temperature in different regions of the sky, and these are referred to as the anisotropies in the cosmic microwave background. And the challenge before us is to understand why the sky has roughly the same temperature in all the different directions. And simultaneously, we need to explain how did this small part, or 1 part in 10 power 5, these anisotropies arose. This, as I mentioned, was a picture taken by Kobe in the early 1990s, about 92 or 94. Since then, there has been many missions, satellite missions, which have observed the anisotropies in the CMB to higher and higher precision. On the left, is CMB anisotropies. What I want you to appreciate is that these different parts, different colors, and the different directions of the sky correspond to differences in temperature of 1 part in 10 power 5 in different directions of the sky. This was a measurement taken by WMAP, and it was done in the 2000s, and in the 2010s there was a more exquisite measurement of the CMB anisotropies by a mission known as Planck, and it has been able to measure this to a much higher precision. So what is the issue? Why do we need an epoch of inflation? Well, the problem is as follows. You have seen this pattern of CMB anisotropies on which I have superimposed certain white patches. I mentioned earlier, the universe, according to our hot Big Bang model, is supposed to have begun in a hot, dense phase. It cooled down as it expanded, and it turned to a matter-dominated phase where there was, energy density of matter dominated the energy density of radiation. And when matter is present, if you put together matter, they will collapse, and they will collapse to form galaxies. That is the rough picture one has, but there is an issue within the hot Big Bang model. What is the issue? I had mentioned that these different directions of the sky have almost the same temperature of about 2.725 Kelvin. And I had also mentioned that these small color differences correspond to temperatures differences of 1 part in 10 power 5. But if you consider the hot Big Bang model, and if you ask what is a causally connected region, if you want a region to have the same temperature, it should have causally interacted with each other in order to achieve that same temperature. But within the hot Big Bang model, what you find is that only 1 degree in the sky. Look at your night sky, take a 1 degree patch of the sky. That is what corresponds to a causally connected region within the hot Big Bang model. And I have indicated such patches in the CMB sky. But the problem is that all these, yes, there are anisotropies. If they were large, if it was 3 degree Kelvin here and 300 here, we would not have worried about it, and we would have said this region has not had opportunity to interact with this region, and therefore these parts of the sky have different temperature. But that's not so. All the sky has, even antipodal regions of the sky, extremely opposite regions of the sky, have almost the same temperature, and this is the problem within the hot Big Bang model. And it is inflation. You have to invoke an epoch of inflation in order to overcome this difficulty with the hot Big Bang model, and this is referred to as the horizon problem. Here, I have tried to illustrate what the horizon problem in a somewhat different picture. You may have, if you have been exposed to some basic ideas in special relativity, you would have seen the light cones drawn. You have a vertical axis, which is time, and the x-axis, the horizontal axis, which is space, and you would typically draw light cones to indicate which are the regions which are causally connected. That is, if you have 2 regions here and they fall within this light cone, you say this region can emit a light ray and influence this light cone, anything that falls within the light cone. So what have we drawn here? This is supposed to be the Big Bang. This is supposed to be the loss scattering surface from which light, the cosmic microwave background comes to us. And this is today, and this is the WMAP satellite. And you can draw a light cone from today to this epoch from which the last scattering surface comes to us. To this epoch which corresponds to the last scattering surface. You can also draw a forward light cone. What you find is that the forward light cone, if you flip this blue cone, you will have a forward light cone. So what you find is that only a small region of the CMB sky, this pattern sky is supposed to what you observe in the CMB. It is only a small region of the CMB sky, this entire sky, which is visible to us from today, which is visible to us from today, seems to be causally connected. That is what I had illustrated in the previous slide. And how do you overcome that and ensure that you can, this whole region is causally connected? This whole region is causally connected at the time of the last scattering surface. Then what you do is as follows. You introduce an epoch of inflation. What it does is that here in the Big Bang model, the time starts in certain units, it starts at 0. what inflation does is that it allows this unit of time to be negative. So you can start at a slightly earlier epoch and ensure you are pushing the Big Bang to an earlier epoch. For those who are technically minded, the vertical axis is the conformal time coordinate. It is for that reason, we are working in a Friedman universe, and it is in the conformal time coordinate, that these light cones go at 45 degrees. So what you need to do is that in the hot Big Bang model, you had the conformal time coordinate remains positive definite, but if you introduce an epoch of inflation, you can ensure this time becomes negative. You can push, in other words, Big Bang to an earlier epoch, and you can ensure that there is a Big Bang is pushed earlier, and you have adequate time so that the forward light cone at the epoch of decoupling is as big as the backward light cone, overcoming the so-called horizon problem. It is referred to as the horizon problem because the size of this light cone, if you flip this light cone, is what is referred to as a horizon, or this is essentially the horizon within the hot Big Bang model. And what inflation does is that it ensures this entire region of the CMB sky is causally connected. So how do you achieve this inflation, or rather, what is the condition for this conformal time coordinate to be negative? Well, you need an epoch of, I mentioned that the universe is expanding. The universe has to go through an epoch of accelerated expansion, very much in the same manner that the dark energy drives accelerated expansion of the universe today. So how do you achieve this? Well, if you have ordinary matter or radiation, you cannot drive accelerated expansion. This again follows from Einstein's equation, which are referred to as the Friedman equations in the context of describing a universe. So you need to turn to some exotic quantity that can allow you to achieve this accelerated expansion. And this is often achieved something called a scalar field. A scalar field is nothing but a ball rolling down a potential, which you would have studied, in a classical mechanics problem. There is only one non-trivial detail that occurs when you study the evolution of a scalar field in an expanding universe. The expansion of the universe slows down this rolling of the ball or the scalar field down a potential. And what one can show is by studying the evolution of the scalar fields in an expanding universe, if you have a potential which has a certain flat region, what you can do is that this flat region, the expansion of the universe will slow down the ball, and this slowly rolling scalar field will drive an accelerated expansion. And what will happen is that even if you start with a fast rolling ball, the expansion of the universe will slow the ball down, even as it tilts through this, even as it goes through this domain where the potential is becoming steeper, and it is only when it has come very close to the bottom of the potential, inflation is terminated, and the field oscillates at the bottom of the potential. And this epoch where inflation occurs because accelerated expansion occurs due to this slowly rolling scalar field is referred to as inflation. And this epoch where the field is sort of oscillating at the bottom of the potential is referred to as reheating, because it is during this epoch the energy from the inflaton is transferred to radiation. I will explain that as we proceed with our discussion. So there are many potentials of scalar fields. These scalar fields abound in high energy physics. One of the popular scalar fields that you may have heard of is the so-called Higgs field. There are many such scalar fields available in high energy physics. You can make use of one of them to drive inflation. And what inflation is as follows. Here is the Big Bang, and time flows downwards here. Very soon after the Big Bang, in fact about 10⁻⁻35 seconds after the Big Bang, what has been plotted is time going down along the y-axis, and the scale or the size of the universe plotted along the x-axis. Notice what happens within a short span of time. Soon after, something like 10⁻⁻35 seconds after the Big Bang, what happens is that the universe increases in size. Remember, the x-axis reflects the size of the universe. The universe increases in size by an extraordinarily large amount. This is due to the accelerated expansion of the universe before it slows down again. And this epoch of accelerated expansion is known as inflation. And what you find is that you can easily see that from this point to this point where inflation starts and ends, the universe would have increased in size by a factor of 10 power 30 or so. What it does, this expansion, is that it cools our universe, and you have to therefore, so I mentioned, I'm sorry, I went in the wrong direction. I mentioned the scalar field rolls down this potential, and as it rolls down the potential, inflation occurs. And as inflation occurs, the universe has become tremendously cool. In fact, it can become even cooler than what it is today. And what has happened is that you need to reheat the universe, and that occurs when the scalar field is oscillating at the bottom of the potential. Notice the scalar field has this much of potential energy, and it is this potential energy that drove inflation. What one can do is that one can transfer all this energy stored in the scalar field into the matter fields, reheating the universe, and that is the epoch referred to as reheating that immediately succeeds inflation. The challenge with inflation is as follows. There are many inflationary models, and one doesn't know how to rule out some of these models. But with the observations of the CMB, there has been better and better constraints on the inflationary models. This is, I'm going to talk about, I have a couple of slightly technical slides for those who are aware of the discussion. What happens is that you have a Hubble scale here plotted in blue, and you have the wavelength of these perturbations. And what you do is that you start with some well-motivated initial conditions motivated by quantum field theory, and you evolve these perturbations. So once you have an inflationary model, you know exactly the kind of perturbation spectra that arise, you know exactly the kind of CMB anisotropies that arise, and therefore you can compare your theory with observations. And what happens is that if you're familiar with some elements of quantum field theory, when the modes are well inside the Hubble radius, what happens is that the wavelength of the perturbations are much smaller than the curvature scale of the universe. When this happens, the modes behave like Minkowski modes, and they oscillate. But once they reach the curvature scale, which is the Hubble radius here, they start freezing. The amplitude of the modes start freezing in the manner I have displayed here. These are the real and the imaginary part of something known as a scalar or curvature perturbation. It is these perturbations in the quantum fields that give rise to the structures that we see around us today, to the CMB anisotropies, and later to the structures we see around us today. As you can see, the perturbations oscillate. Perturbations are deviations from a homogeneous background, and they freeze in their amplitude as they leave the Hubble radius. Apologies for the non-experts about these couple of technical slides. So what do? I mentioned that it is these perturbations are generated due to the quantum aspects, quantum contributions from the scalar field, and it is those quantum contributions that are supposed to lead to the anisotropies in the cosmic microwave background that I showed pictures of earlier. And what you do is that there are two types of perturbations that are generated. One are essentially density perturbations. They are called as scalar perturbations. That is what gives rise largely to the anisotropies, and much later it is these density perturbations that give rise to the structures in the universe, namely the galaxies and clusters of galaxies. Apart from the scalar perturbations indicated here, you have something known as tensor perturbations as well. Tensor perturbations are essentially gravitational waves. If you have studied some aspects of gravitational waves, you will learn that gravitational waves can be generated in an expanding universe, even in the absence of sources, if you have some quantum initial conditions, and these are known as primordial gravitational waves. And one of the holy grails of cosmology is to detect these primordial gravitational waves. And these primordial spectra that that are generated during inflation are characterized by these four quantities, typically AS, NS, AT, and NT. What is amazing is that we have been able to measure some of these quantities to extraordinarily great accuracy over the last decade or two because of the CMB missions. And what one is focused on currently are the following quantities. We know this AS very well because we know the amplitude of the anisotropies in the CMB, and we amazingly know NS also quite well. And what we are interested in, we are at this stage not interested in NT because we still haven't seen the imprints of the tensor perturbations, or what are known as the primordial gravitational waves. They are generated in the early universe. They are inescapable, and you calculate the ratio of essentially this AT here to AS. Since we know AS very well, you define something called the tensor to scalar ratio, and what one is interested in cosmology today is arriving at a good understanding of what RK will be. And as we will see in the next slide, or in a slide or two later, we have a good understanding of what NS is. This is what is the CMB angular power spectrum from Planck. All one has done is that, I'm sure many of the people here are familiar with the idea of Fourier transforms. The Fourier transform is typically done in a single dimension or in many dimensions. If you Fourier transform on the surface of so you have to decompose in terms of normal modes on the surface of a sphere. You have what are known as spherical harmonics. So these are essentially the Fourier amplitudes of the CMB anisotropies that I had shown earlier. These red dots are with error bars are the observations, and this line, blue line here, is what is predicted by a simple inflationary model, what are known as slowly rolling inflationary models. Remember, I had said earlier that the scalar fields will roll down an inflationary potential, and the expansion of the universe will naturally slow them down. And this blue line is a spectrum generated in a typical inflationary model, simple slow roll inflationary model, and evidently the observations match. The theory matches the observations fairly well. And this is again a slightly technical slide, but if you're interested in what is an inflationary model that fits well with the data, it is the so-called, what is referred to as an R-squared inflation, or the Starobinsky model, which lies here. We know this primordial tilt, or NS spectral tilt, which is close to NS. NS is 0.965 or so, and the Starobinsky model indeed predicts some value close to 0.965. And what we have is the upper limits on what is the contribution of what are the contributions of the gravitational waves to the CMB anisotropies. These are constrained or water large scales. Cosmological scales roughly correspond to about a meg or so. I'm assuming that people are familiar with what a megaparsec is. Megaparsec is 10⁶ parsec, and a parsec in turn is about 3 light years. So cosmological scales correspond to large scales which are probed by the CMB that I've talked about, correspond to scales of the order of about something like 1 megaparsec to about 10⁴ megaparsec. 10⁴ megaparsec can be said to be roughly the size of the observable universe today. And there are expectations that we may be able to observe some features of primordial physics on smaller scales as well, which is what I would turn to. Before I go on to discuss this physics over smaller scales, what one is interested in, I said that you have a nearly scale invariant spectrum as described by a line something like this, which fits the data very well. This is the primordial spectrum. This is the spectrum. This is the characteristics of the deviations from smoothness which are generated from quantum fluctuations at the end of inflation. And it is amazing that we are able to say some, we are able to understand the characteristics of this. And there has been an interest in understanding whether it is indeed nearly flat or whether there are deviations from it. And if there are deviations from it, we will be able to arrive at constraints on the primordial physics, or equivalently the models that drive inflation better. And there has been considerable investigations in this context, and one of the investigations involved where the primordial spectrum has a sharp step like this, and we will see such sharp steps but shifted to smaller scales can lead to what are known as primordial black holes, and that has been of considerable interest over the last few years. I will explain the reasons in a matter of minutes, and before that I will make a few remarks about how do you generate such large steps in the primordial power spectrum. Recall, I had been mentioning about how a scalar field evolves in an inflationary potential. Here is how it evolves in a simple inflationary potential. This is actual evolution. Earlier, it was a cartoon diagram. It has been plotted at equal intervals of time, and in a simple inflationary model that is driven by the so-called Stravinsky model, the scalar field evolves in this manner, and the blue part corresponds to inflation. Inflation gets terminated when the field is somewhere here, and it oscillates at the bottom of the potential, something I have explained earlier. But what you can do is that you can introduce some strange features in your potential. You can introduce what are known as points of inflection, where the potential derivative, first and the second derivative of the potential vanishes. If you do so, you can enhance power on large scales, and I will explain the reason for considering such models and why it has become important and interesting to study over the last few years. So this is again a couple of technical slides for those experts. So what I have been plotting here is essentially here, please note this curve here, and please look at this figure. This figure should be familiar to any physics student. What has been plotted here is essentially the phase portrait of something like a damped harmonic oscillator. What will happen is that its velocity as the oscillator, as the ball rolls down an harmonic oscillator potential, and if it is damped, it will come down and roll along, about the center. And this is the phase portrait. Remember, this is light position, this is light velocity. Its velocity comes down, and eventually it falls in the middle, falls to the origin. That is essentially what has been plotted here. We have plotted the behavior of the scalar field, but there is some non-trivial dynamics involved here because of this point of inflection. What happens is that, notice the field rolls down this potential. You have chosen your potential. It is obviously not a simple harmonic oscillator potential. Suddenly, what happens is that the velocity of the fields considerably comes down because the potential becomes extremely flat. The first derivative vanishes, the second derivative vanishes, and therefore it almost comes down to a halt. It just barely escapes through and comes to the bottom of the potential, rolls down and falls in the middle. And what happens is that the velocity of the field drastically decreases before it increases again to end inflation at the bottom of the potential. I will ignore this slide. And in such a case, what you can do is that I had earlier mentioned that if you have a slowly rolling potential, you will have a nearly flat primordial spectrum, which I should mention has been suggested, much before even inflation has been proposed. And typical inflation models will lead to a spectrum that is nearly what is referred to as nearly scale invariant. Remember, NS was 0.96 and NS is equal to 1 implies a scale invariant primordial power spectrum, which implies that there is almost equal power on all scales, which is generated by the primordial quantum fluctuations. But what happens if you have a point of inflection and the dynamics of the scalar field behaves in this manner, where the velocity of the field decreases considerably before it increases again and inflation comes to a halt? What happens is that there is a sudden rise in the power. There is a sudden rise in the power, and we will see its implications of such a rise in the power and why people are interested in it over the next 2 slides. What happens is as follows. It is not only, I have talked about single field models. This is just details. You can generate them in 2 field models as well. And you can generate features where there is sudden excess power in certain models over small scales. Remember, these are the scales, cosmological scales. The cosmological scales are here, scales of the order of 10 power minus 4 megaparsec inverse to about 1 megaparsec inverse is cosmological scale, which are probed by the CMB. This part is not probed by the CMB physics, and hence, if you want to understand the dynamics of the scalar field during inflation, you need to turn to other observation. This is where these objects called primordial black holes and secondary gravitational waves come in. What happens is as follows. I had talked about the evolution of the modes earlier. Here is a picture. You have a Hubble radius during inflation, which is roughly a constant. Modes leave the Hubble radius. And the fact that these modes are outside the Hubble radius, if you have only an epoch of radiation domination here, is what is referred to as what we discussed as the horizon problem. But in the context of inflation, that if you have an epoch of inflation followed by an epoch of radiation domination, then these modes will re-enter scales. Most of the scales of interest, at smaller scales of interest, will re-enter the Hubble radius during radiation domination. If these modes have enormous power, the moment they re-enter the Hubble radius, what will happen is that they will collapse and form black holes. And these black holes, which are formed during the radiation-dominated epoch prior to the epoch of decoupling, are called primordial black holes. And why are we interested in it? Well, I could have gone in this fashion. And why are we interested in this? Remember, I had shown you a few slides which had, excess power. This is the power that explains the CMB anisotropies. What we have done is that on scales which are not sensitive to the CMB anisotropies, we have enhanced the power considerably. And what do? They tend to form these black holes. And what has been plotted here is the fraction of these black holes that constitute the dark matter density today. I'm sure you have heard about the fact that, there are dark matter present in the universe, and we don't exactly know what is the nature of this dark matter. One form of dark matter could be these primordial black holes that have formed in the early universe. And in certain models, they can form as much as about, 10% of the dark matter in the universe. And this is why this has become attractive. And why are you interested in these primordial black holes? Well, you would have heard about the observations of gravitational waves from merging binary black holes. And amazingly, what one finds is that many of these black holes that have been observed by LIGO fall in the range of about a few tens of solar masses, solar masses, and often such solar mass black holes are difficult to explain within the astrophysical domain. And there has been an interest to examine whether these black holes could have a primordial origin. And what I have illustrated is that yes, certain inflationary models can produce primordial black holes of significant numbers, such that they constitute about 10% of the 10% of the dark matter density today. What is interesting is as follows. Let me go back to this evolution of the modes. I said these modes re-enter the Hubble radius, and they have enormous power on those scales. Let me illustrate the strength of the power. Remember the power spectrum. Here you have about 10 power 8 or 10 power minus 8 or 10 power minus 9. Here at the peak, they are about 6 to 7 orders of magnitude larger than the power on these scales. What happens is that when they re-enter the Hubble radius, as I mentioned here, they also generate what are known as secondary gravitational waves. I mentioned that inflation generates gravitational waves, which are perturbations, which are referred to as tensor perturbations, and they are inevitable. If you have situations where such black holes are produced, they inevitably produce gravitational waves. And what has been plotted are the observational consequences of power spectra such as this that I have displayed here. What has been plotted is the energy density of the gravitational waves today, plotted as a function of frequency. I'm sure you may be familiar with the fact that LIGO operates at a frequency about 100 Hertz. There are many gravitational wave observatories that are being planned over a wide range of frequencies, through either direct observations such as this or through indirect observations such as pulsar timing arrays. And what is interesting is that if you want to generate such large black holes, these models also end up generating enormous amount of gravitational waves. These are in the single field models, these are in two field models, and these in principle can be detected by future observational missions. And this is what one hopes, that apart from the CMB physics, there could be other physics that can help us understand the physics of the early universe. I have about 5 odd minutes. In the last few minutes, I will talk about this observational signatures of this epoch of reheating. What I have plotted is a slightly different quantity. I had plotted here the evolution of the modes. In an expanding universe, the wavelengths of the perturbations are always proportional to the scale factor. This is the logarithm of the length scale plotted against the logarithm of the scale factor, or often referred to as E-fold. What happens is that these, as I said, these perturbations are generated and they evolve. You can instead plot another convenient quantity, which is what is known as the co-moving length, that you take this length and divide by the scale factor. So you divide the Hubble radius by the scale factor, and you divide the physical wavelength by the scale factor, and you will arrive at what is known as a co-moving wavelength. And that is what has been plotted here. So you have different wave numbers. These are the wave numbers that correspond to the wave numbers today. And what has been plotted are scales that can be observed during inflation, and that goes from cosmological scales corresponding to a few hundred megaparsec today to extremely small scales today, which can, whose primordial imprints can be detected in the gravitational wave spectrum. And you can have, what has been plotted is the co-moving Hubble radius and the co-moving wave number. The wave numbers are constants, and the co-moving Hubble radius decreases rapidly in this picture. And this is, of course, logarithm of the scale factor, which can be considered as time. And you have an epoch of inflation followed by an epoch of reheating, and then you have non-trivial scenarios. What we have examined is what happens to the primordial gravitational waves if you have an epoch of reheating. Remember, I had explained reheating as the time when succeeding inflation, when the scalar field is rolling at the bottom of the potential, and during this epoch, the energy from the inflaton is transferred to radiation. And we have examined different models, and I have plotted the same omega GW h squared, that is the energy density of gravitational waves. This is no different. This is not very different from the energy density of electromagnetic waves that we are familiar. All you need to do is that take a gravitational wave detector, make it sensitive to all directions of the sky, and if you start, measuring what is known as a stochastic gravitational background, these are background that are present, and these are, and you cannot erase them in any manner. So if a LIGO or another future detector, such as the Big Bang observer, is sensitive, sees the stochastic gravitational wave background, you will be able to understand the physics as it operated on the highest energies in the very early universe. I want you to appreciate that these energies cannot be accessed by terrestrial experiments such as Large Hadron Colliders and others. So what happens? You have the gravitational wave spectrum here plotted, or rather the gravitational spectral energy density, and what here is the epoch of reheating, and we hope that, future observatories may be able to detect these signatures and help us understand what happened very early in the universe. And what we have here is another scenario. There can be scenarios, non-trivial scenarios, where in principle they can even explain a signal that has already been observed. I mentioned there are direct detection of gravitational waves, and there are also indirect detection through something called the pulsar timing arrays. And there has been an argument to suggest that what is detected by something known as nanograv could be a stochastic gravitational wave background. Here we have constructed a mechanism that can possibly explain the signal that has been observed by nanograv. So with that, I will come to the summary of my talk. What I have been trying to say is that increasingly precise observations of the anisotropies and the spectral distortions of the CMB, as well as observations of the distribution of large-scale structure, are expected to help us arrive at stronger constraints on the primordial power spectrum over large scales. Observations of the stochastic gravitational background, by what I just discussed towards the later part of the talk, by either ongoing or forthcoming gravitational wave observatories, can help us constraining the primordial power spectrum on small scales. So it is hoped that these complementary observations over a range of scales, from large scales from the CMB on small scales from the gravitational wave observatories, will help us understand the physics of the early universe, specifically the epochs of inflation and reheating. With those remarks, I will stop here, and I will thank you. And I thank you for your attention. Sir, I'm glad to, I'll be happy to answer questions, sir.
Yeah, thank you, Professor Sriram Kumar, for sharing your memories with Paddy, and also for your erudite lecture. And I understand that you have taken a lot of effort in explaining the most complex cosmos phenomena in a popular science manner. Thank you. Now it is time for interaction.
I think our science mentor Dattan sir is in line. Sir, few words.
Thank you very much. I was very patiently listening to the talk, though I am not a physicist man. As a rocket scientist, our interest to the subjects of the great scientist was gravitation. Wherever the gravitation things comes, we listen to it, and also the gravitational wave. The gravitation, as we understand, it is time and space dependent. We have a very peculiar experience in that in the Chandrayaan-2 failure, partial failure there. The first time, we were trying to have a landing on the south pole of the moon. And really, the gravitational characteristics of the south pole of moon could not be fully characterized, studied by anybody. That was one reason there for the failure also. So I recollect when you was talking about all those things, I was recollecting our experience. Second thing, I just want to get a clarification from the learned expert like that, the gravitational wave was physically, we all could confirm to it by 2016 February. My question is, before that, before 2016 February, with the available knowledge, etc., what was the indication about that? And later, how we could ascertain it? If you can just throw some light over it, I'll be happy to listen.
Sure, sir. There was something known as the Hulse-Taylor pulsar. The classic Rutherford model of the atom, right? It failed because you have an accelerated charge that is moving, and the accelerated charge radiates and loses energy, falls into the center. And you would have heard that the Rutherford atom model fails because of this reason. In very much the same manner, if you have two bodies which are moving around, what happens is that they emit gravitational waves, they lose energy and start coming closer to each other. It is just that it's a very slow process because the amount of energy lost in gravitational waves is not significant. There is something known as a Hulse-Taylor pulsar. There is a two-binary pulsar, which they have been able to follow extremely closely for 30 years, I think from 1976 onwards, and they could ascertain the way in which they were moving around, and they could explain the motion and the fact that they were losing energy and coming closer to each other to the fact that they were emitting gravitational waves. And for this, Hulse and Taylor won the Nobel Prize much before the actual direct discovery of gravitational waves. You need to make a distinction here. The Hulse-Taylor observation was an indirect discovery. That is, you explain the motion of this pulsar, binary pulsar, two pulsars moving around each other through the fact that they are emitting gravitational, the system is emitting gravitational radiation. What happened in 2016 was that they actually detected direct observations of gravitational waves with the help of this LIGO observatory. I hope I've been able to answer your question.
Yeah. It's clear now. Yeah. Thank you.
You're welcome, sir.
Sir,
May I?
Sir, our Honorable Chief Secretary, Dr. V.P. Joy, has published a poem in Kala Kaumadi Malayalam prestigious magazine in the latest issue, September 26 to October 3rd, in the title Bhautikayanam. I will just, for the interest of audience, I will just recite its initial words. He was kind enough to send it to me.
Sure, sir.
Maybe I also request Dr. Harinarayanan to project it so that others, പ്രപഞ്ചത്തെ അറിയുവാൻ വിഴിക്കുന്നൊരുൾ കണ്ണിലി പ്രപഞ്ചമുണരുന്നു വളർന്നിടുന്നു ചലനമാണെങ്ങുമൊപ്പം ഗുരുത്വവും അതെന്തെന്നു വികസ്വരമാകുന്നെന്റെ ഭാവനാ നേത്രം സ്ഥലകാലം മൗലികമാം സർവവ്യാപി സ്ഥലകാല വക്രതയ്ക്കു ഹേതുവാകുന്നു. It goes like that, and it ends like this. അറിയുമ്പോൾ അറിയാതായി രൂപം മാറും പ്രഹേളിക, അറിയാതെ അറിവാകും വിശ്വസങ്കൽപ്പം. അറിയുവാൻ താണു പത്മനാഭ സവിധത്തിൽ നമ്മൾ തൽസാമീപ്യം സത്യവിസ്മയം. This is a great tribute to Professor Thanu Padmanabhan. We will continue with interaction. I think Professor C.P. Aravindashan sir was raising some queries. Sir, please.
Please unmute all so that they can raise question. Or Titus sir, you can ask question now.
Okay. Hi, Sriram.
Hi, Titus. Good to see you.
Yeah. What I want to ask is, there are some models called running vacuum models, in which the authors trying to unify inflation with late acceleration. So, what's the problem if you are using cosmological constant in explaining inflation? What is the difficulty then?
Oh, the cosmological constant, yeah. The cosmological constant, what happens is that the perturbations decay rapidly. In a strict cosmological constant, the perturbations decay rapidly. But the moment there is a small deviation from it, that is, it is not strict de-sitter, but slow roll, then you are... Is that what I said clear, Titus?
Yes, yes.
Okay.
Yes.
So it is, the cosmological constant is somewhat pathological. You will not be even able to define perturbations properly, scalar perturbations, for instance, properly. And also they will quickly decay in a pure, if it is purely cosmological constant dominated universe. That is why, for instance, at late times, when you consider pure de-sitter or pure cosmological constant, people don't worry so much about the perturbation. The moment you have dark energy, small deviations from de-sitter, then you need to take that into account. That's one point. The other question concerning what you asked, whether you can have the same scalar field driving inflation and late time acceleration. Yes, there are some models. For instance, a popular model by Gundelman is one of the first authors. I don't recall the complete potential. They had a model which seems to do fairly well, and in fact, it won the second prize in the gravity essay context. And I also recall a recent paper. Unfortunately, I haven't paid close attention to it. I may have it somewhere saved. Is a model very much like the like the models with inflection points that I talked about, which has been considered in the context of explaining both inflation and dark energy. So there have been some efforts in this direction. I think the challenge is extensive fine-tuning involved to make sure that inflation occurs at a particular scale and dark energy dominates at a different scale.
Thank you. One more question,
Sure.
Sriram. See, in the context of Padmanabhan's theory, emergent gravity, it has somehow they wrote a paper in Physics Letters B, deriving the cosmological constant with his daughter. So, can they address the problem similarly of inflation? Is there any?
So there is, yes, there was a paper where they tried to match this. Okay, I am not, how it emerges from the emergent gravity paradigm has not been very clear to me. I'm not quite I haven't paid too close an attention to the Paddy's emergent paradigm. Maybe Dawood, who will speak a few days later, will be able to comment about this. Okay, so I am aware of this paper by Paddy and Hamsa about matching numbers so that they are able to explain inflation and the cosmological constant. But I think that the fundamental question is whether they are genuine or whether they are coincidences, right? I mean,
my question is whether they can is it possible to address the issues in inflation using that. Okay, maybe
So
I
you
can
cannot
ask to.
quite, yeah, that would may be able to answer better, because to my knowledge, the emergent gravity paradigm that that people motivate from the thermodynamic perspective, right?
Yes, yes, yes.
Look, they have never argued about d zeta cosmological horizons. To my knowledge, they have talked always about black hole horizons.
Yes, yes.
So there may be some technical challenges in implementing the idea to cosmological horizons. Dawood should be able to answer that more.
Thank you. Thank you.
Better.
Thank you, Sarira.
Yeah, pleasure.
Indication, sir, please.
Question, you mentioned that black hole or black matter is contributing to black energy. In one of the slides you are mentioning.
I mentioned primordial black holes can contribute to dark matter.
How is it?
So essentially, what is dark matter is something which behaves very much like matter, doesn't emit much light or interact much light. Black holes, if you have a collection of very massive, very compact objects, they will satisfy what is known as the same equation of state as dark matter. And they will essentially, whole dark matter is something which just interacts like balls of matter. They don't have exert any pressure, etc., like radiation. So if you have a collection of black holes, they will behave very much in the manner like small particles, massive particles, which are interacting with each other only through gravity. And therefore, primordial black holes, for instance, if you have brown dwarfs in the universe, that is, if you have stars which have collapsed but have not, have adequate temperature in the center to, initiate nuclear fusion, these are referred to as brown dwarfs. They all, in principle, can contribute to dark matter, essentially, matter which behaves like ordinary matter but does not, emit light. In that sense, primordial black holes can act as dark matter.
No gravitational waves are generated there.
Sorry.
No gravitational waves.
So what happens is that you have to understand the following. So gravitational waves can be okay. You need to explain this cosmic microwave background anisotropies. Why are they present there? And the only way you can explain them is through quantum fluctuations. Quantum fluctuations are completely unavoidable, and therefore they will always be present. And it is actually those quantum fluctuations that gave rise to those anisotropies. And these anisotropies later led to galaxies. So in some sense, we have originated from quantum fluctuations in the early universe. These quantum fluctuations, since at some level, even gravity has to be quantized. If you try to quantize these what are known as tensor perturbations or gravitational waves, they will be present, they will be generated in the universe. There are two ways of generating them, gravitational waves. In fact, there are multiple ways. I had focused on two mechanisms. One through what is known as quantum fluctuation, which originate in the early universe, okay, and another which are sourced by matter present in the universe. Just like two black holes going around can generate gravitational waves, if you have distribution of matter which is sloshing around, they can also generate gravitational waves in the early universe. Both can, in principle, can be generated in the early universe. And what will happen is that, imagine if you have a detector which is just buzzing zzz, like that, you have a gravitational wave detector, and if they are of enormous strength, your gravitational wave detector will not remain silent at all. It will be buzzing at a certain amplitude, and that is essentially what is referred to as the stochastic gravitational wave background. Just like you have a cosmic microwave background in light, there is a gravitational wave. There is a background in gravitational waves, and that may have many sources. And one is trying to understand what are the different sources, whether we can detect them, and therefore understand the physics of the early universe.
Okay. Thank you. Thank you.
My pleasure, sir.
Any other questions, please?
I noticed there is a hand raised by Dr. Mamta Sahu.
Mamta Sahu, please.
Yeah, you can ask your doubt.
Madam, you can unmute yourself. It's already. I think she is not there.
No, she's there, I think. She's there.
No, sir. She's not there.
Yes, she has raised her hand, but she
Yeah.
doesn't pick it.
She's there. She's there.
Probably she might be speaking in the mute position. That is.
I think so. She has to unmute herself there. Dr. Mamta Sahu, can you just unmute yourself? Sunil, please try to unmute from this side. No.
Maybe anybody else? Any other questions, please? Any other points to be added or supported or questioned rather? Pradeep sir?
Yes, we can conclude
Sir.
if no other questions are there.
Yeah. So we are coming to the conclusion part. Now may I request Dr. P. Harinarayanan, Principal Scientist, KSCSTE, and also co-convener of the program to propose formal vote of thanks.
Respected President of the Function, the Member Secretary of KSCSTE, Dr. Pradeep Kumar, Chief Guest of the Function and the Chief Secretary of Kerala, Dr. V.P. Joy, sir, Professor Somak Chaudhary, Dr. L. Sriram Kumar, Sri M.C. Dattan, sir, distinguished other guests, eminent professors, scientists, and my dear colleagues. We had an excellent day today remembering the great scientist of the country, Professor Thanu Padmanabhan. Professor Thanu Padmanabhan had a very close association with the Science and Technology Council. He has headed the scheme for the scheme called Selective Augmentation of Research and Development, the SARD, what we have. He was the chairman of the committee for a long time. He was always with us in Science Congress. And based on his contribution to the country in science field, the state has selected him for the best Shastra Puraskaram for the lifetime achievement in science. And today we have honored him, paid tributes to him by conducting the webinar, and we'll be continuing for the next 4 more days. Now I'm coming to my duty. Dr. V.P. Joy, the Chief Secretary of Kerala, has inaugurated this webinar series by delivering the inaugural speech, by paying tribute to the great scientist and explaining the work done by Professor Thanu Padmanabhan in a very simple way. We are grateful to you, sir, for inaugurating this webinar series. More than that, the poem written by him has been published recently, which is paid tributes to Dr. Professor Thanu Padmanabhan. It was also read out here. We had Professor Somak Chaudhary, who had paid tributes to Professor Thanu Padmanabhan by narrating his association, a long association of 35 years as a scientist, as a colleague, and he was mentioning the about Professor Thanu Padmanabhan as a, not only as a scientist, he's a author of many books. He was a science popularizer, and I thank Dr. Soma Chowdhury for being with us and paying tributes in this webinar series. So thank you, sir. Dr. L. Sriram Kumar has remembered the days he has associated with Professor Thanu Padmanabhan and also his family. He had delivered a talk, though it was with respect to physics. Even a person without the physics background could understand what he has mentioned about the universe, about the physics of universe. So thank you, sir, very much for giving us such an excellent lecture. Thank you very much on behalf of KSCSTE and all the organizers and all participants present here. We had Professor M.C. Dattan, Sri M.C. Dattan, the science mentor of the Kerala government, and who has been always an inspiration to KSCSTE and was supporting KSCSTE in conducting such programs. Thank you, sir, for being with us. We had many eminent professors, Professor Unnikrishnan Nair, Professor Titus, and many other persons from many different institutions, and many scientists from different institutions of the country. I thank one and all for being with us. I thank my colleagues, especially Dr. Ajit Prabhu sir, who has been coordinating all these activities, all other colleagues who have been with us. I should also thank Professor K.P. Sudhir, who is not with us because of some personal issues. He had been the inspiration who has been behind this program from day one onwards. So I thank him also. I thank all others, especially the team who had been working behind this program, Rohit, Sunil, and all others. I thank one and all. Thank you very much. Thank you all.
Let us all assemble tomorrow at 3 p.m. for the second commemorative lecture in this series by Professor Shankara Narayanan, Professor, Department of Physics, IIT Bombay. Thank you, Pradeep sir, for presiding over this function. Thank you very much. Request you to conclude, sir.
Thank you. Thank you. We may conclude the meeting by this formal vote of thanks. Thank you all.
Thank you.